Good afternoon, thank you very much. Last presentation of the day, so I hope it's worthwhile for you to stay this long. This presentation I did together with my colleague, now former colleague Nico Burgelman, who is in the audience also. I'm going to tell you something about damage function development using a twin disk machine. Well, it works. Introduction, something about the aim of the research, going quickly into the setup of the testing and results and some conclusions. It's all aiming on understanding rail performance mainly, because if you want to achieve an improved rail performance, you have to understand the material response towards the loading. And from this understanding, you can go to a fit-for-purpose approach, maybe reducing or adapting loading levels to the rail grades that are in track, for instance by track-friendly trains, or lubrication could also help, and also improving the loading resistance of the material itself, so put in new rail grades that are up for the job. So fine-tune your rail grade selection strategy, I would say. Helping to understand the performance of rail grades and also the loading response is one of the features is the concept of the rail damage function, as developed by Burstow. This is one for R220 material. It helps you to understand the response of the material. It's the wear number, or T gamma, basically the work that is performed by the frictional forces in the moving contact patch is set out here and together with the damage development or damage rolling contact fatigue, or better head check initiation at the contacting surface. Now this image can help you to understand the response of the material. For instance, are we below or at the fatigue threshold? There's no damage to be expected. Maybe we are in the rolling contact fatigue initiation area, so rolling contact fatigue damage is to be expected. You could be at the transition to the wear, or maybe far out into the wear regime, from which you probably can expect excessive wear. This function really helps, and recently it also has been extended to a premium rail. As I explained, the previous one was for standard R220. This work has been done by also by me and by Michael Steenbergen to look at the development. Could we develop these functions also for premium rails? And it has been done, like the previous one, from track inspections together with simulation work. But it is quite difficult to do this only from track inspection and simulation work because of the big variety in loading parameters outside. So we were thinking, is there a possibility also to support this with laboratory testing, in which we can select a very targeted T gamma value and then understand the loading response. And that's exactly where this presentation is all about. So the aim was the validation of a two-disc test approach to define the wheel-rail interface wear and rolling contact fatigue response. So this is the setup, more or less. We selected the wheel contact of the contact dimensions and also the normal stresses according to those that normally occur in track at head check sensitive locations, I would say. It's a 1 in 5 scale, both longitudinal and lateral slip. The lateral slip is achieved by tilting an angular rotation of one of the discs. This, I don't know if the pointer works. No, okay. Wheel disc, the rail disc, and the rail disc is mounted on a plateau that can change, but you can also tilt this one. So in that sense, you can give a lateral slip. Contact speed is set here. We can measure the coefficient of friction by measuring the torque. The rail material we used, the rail disc, is a R220 because the validation was mainly aimed to look at if we could reproduce the Burstow figures, more or less. Okay. Well, since we're working at partial slip, we needed to understand the operational friction coefficient, and we used this approach calculated from the FastCML algorithm. So setting up the test, and then from that, from the set longitudinal slip and the measured torque and the measured normal force, we could then understand what the operational friction coefficient is, and from this operational friction coefficient, together with the normal force and the disk curvature and the set slip levels, we can go to the T gamma level we want to test. Jasinski previously has concluded that T gamma scales proportional to the normal force, so we could make an equivalent T gamma in this case for a 9-ton wheel load. So this graph is really used to set the operational point during our testing. The procedure looked a little bit like this. So there was a run-in period, so there was some work hardening could be done. After that, longitudinal slip was applied. We gave the friction coefficient time to settle in a little bit. And according to the friction coefficient at that time, we can set the T gamma with the slip level, the longitudinal slip level, and then multiple sessions were run. We stopped every 20,000 cycles to observe the contact. Look at crack length development, looked at profile development, hardness, and also roughness. And now we can start a movie, which is always nice. So this is in a room outside the main office, because it can generate a lot of noise. We used to use the same apparatus also to test for squeal noise, so it's very good that we have it outside our laboratory. Then I come to the assessing of the rolling contact fatigue life. As I said, we use a visual assessment together also with some eddy current measurements. But basically it's a visual crack detection, just like has been done by the Burstow approach outside. There we use a 2 millimeter minimum crack length to set the data points. Because of the 1:5 scale, we use the 0.4 millimeter here. Here you see some crack development in the surface. What was very striking is that we managed to find rolling contact fatigue development in the part of the rail disc that was machined from the rail head. But in the rail web and the circumferences that was also in the foot of the rail, no cracks occurred. So that was really a first striking difference. Here you see some images. This is of one of the cracks, of flakes, you would say. I think if we could test them also together with some water lubrication, we could make them grow. But for this research, we were basically interested in the initiation of cracks, not directly the growth of cracks. You see a big difference between the material in the head of the rail, the perlite structure with some ferrite on the pre-austenite grain boundaries. The other picture is the microstructure at the web, and in the foot it looked basically the same. You see much more free ferrite, and this is also reflected in the hardness and also in the wear development we measured from the profiles. The web area was 1.7 times more wearing than the head area, and I think that is also could be the explanation for the absence of the cracks, because this is shifting it into the regime which is fully dominated by the wear. There was also some evaluation on the contact conditions, the mini-prof measurements before and after. So there are some changes, and we wanted to understand how this would affect the contact conditions. Given this change in contact, we could not do it with the Hiensch contact of approach. So the Kalkar full theory was used here to calculate for the contact stresses and also for the T-gamma values. Now you can see that there is some changes have occurred during testing due to these deformations. But if we look at the T-gamma, the effect on the T-gamma calculations, what does this mean for T-gamma? We see almost no difference or no difference. So for the T-gamma values, the change in contact in profile conditions was not very strong. So that gave us the confidence that we have been testing all the time at the targeted levels. So this is basically the validation results. Here you see some changes in roughness during the testing, friction coefficients. These numbers behind here, these illustrate the run numbers. So from that you can see a little bit how the development was going on. Basically what you can see here, that at the T-gamma of 65, we tested directly in the top of the rolling contact fatigue function. So these 2 points are quite good. And also we did some tests at the 120 level. And again, we found we observed very good correlation with the Burstow function. So from the test results we have obtained so far, it looks like we can reproduce the figures that were found by Burstow in track in combination with simulations. There were some other observations that for all the tests we did, in the end, the friction coefficient was seen to stabilize at 0.2. So it seemed that it was not really influenced by the amount of slip we put on. Well, I have to say that the slip levels, of course, are small, but we did not see any changes in friction coefficient. And when we shifted also to the higher T-gamma values, we saw that there was a wavy pattern occurring at the rail disc. And this could potentially also influence the testing results. But at this time, the wavy pattern was very small. But I expect that if we go to even further T-gamma values, it could be developed stronger. So we have to look into that, how we can possibly prevent this periodic waviness or polygonization, how we could prevent that. So to the conclusions, I think from the functions we have found, it seems that the validation results suggest that this approach can work to support the future work of establishing rolling contact fatigue damage functions in a defined laboratory environment. So it seems very successful at this point. Thank you very much.